Good afternoon. Good afternoon and welcome to the University of Alcalá for this 25th conference on organometallic chemistry. In first place, I am going to give the floor to Professor Dr. Antonio Echevarren, President of the Royal Society of Chemistry in Spain. Antonio?
Thank you, Senor Rector. So it's a pleasure just to be here opening this conference on organometallic chemistry. I would like to thank Marta Mosquera, Ernesto de Jesus, and the rest of the organizing committee and the University of Alcalá for having organized this meeting. I would like just to quote three important names in chemistry. First one is Dieter Sebach, for his famous review titled Organic Synthesis, Where Now, that was published in 1990. In this famous review, Dieter Sebach mentioned that the discovery, I'm quoting literally, of truly new reactions is likely to be limited to the realm of transition metal organic chemistry. This is the way he called organometallic chemistry, transition metal organic chemistry, which will almost certainly provide us with additional miracle reagents in the years to come. As regards main group element, organoelemental chemistry, we can surely anticipate further stepwise improvements in experimental procedures and the broader application of special techniques, leading to a dream of efficiency and selectivity with respect to known procedures. This is the quote. Despite the development of organocatalysis and the rediscovery of photochemistry and radical chemistry in the context of photoredox catalysis, Sebach's vision is still essentially true. So most of the innovation in catalysis or homogeneous catalysis comes from this field, from the transition metal chemistry. However, still there are many reactions and miracle reagents remain to be discovered for important reactions like selective CH activation reactions and nitrogen fixation and many others. Regarding where we are in chemistry, chemistry is considered to be a mature field by many. It's important also to quote the words of an organic chemist, Gilbert Stork, who passed away only a few years ago. He said that, literally quoting, so it is not surprising that organic synthesis, but probably this applies not only to organic synthesis, but to chemistry in general, is far from the level that many people assume. Progress is continuing, but there will not be any dramatic developments. It is more like a glacier that gradually moves forward until it has been finally covered an entire region. So this is the way chemistry moves, slowly but continuously. But it will still be centuries before synthesis has acquired the status that many people already ascribe to it today. And this, I think, also applies to organometallic chemistry. And finally, quoting George Whitesides in a paper published in 2018, it was an account. He said that catalysis is an exceptionally interesting problem. One can argue that chemistry is, in a sense, mostly catalysis. And life, as a dynamic dissipative process, is almost entirely catalysis. Given its importance, it is astonishing how difficult it has been to discover fundamentally new classes of catalysts, and even to mimic and extend the structures already known. Although catalysis by metals has been a central theme of organic chemistry for decades, it has tended to focus on a limited number of subjects. This is a critical view of the field. There is still almost no progress in mimicking the characteristics of enzymes. So there is plenty of room for us chemists to really achieve the goal of mimicking what enzymes do by inventing new miracle reagents and catalysts. Organometallic chemistry in Spain, both coming from the inorganic and the organic tradition, has been the bow of the chemical boat of chemistry in Spain, with leading figures, heroes, such as Rafael Usón, Marcial Moreno Mañas, José Barluenga, Luis Oro, Pascual Royo from this university, Luis Oro, Víctor Riera, José Jimeno, Ernesto Carmona, Pablo Espinet, Pedro Pérez, and many others. The Organometallic Chemistry section of the Spanish Royal Society of Chemistry of Spain, has also played one of the leading roles in our chemical society, having contributed to the current status of the society, of the Spanish Chemical Society, as being the most important scientific society in Spain, and one of the most important chemical societies in Europe. Despite the heavy rains that we have all enjoyed yesterday and today, I think we can predict that we have now much better weather for sure. I'm sure that this conference will be a success, showcasing the state of the art of this dynamic field of organometallic chemistry. Thank you.
Thank you, Antonio. Now, Professor Martin Albrecht, President of the Chair of the EuCOMC Division of Organometallic Chemistry, has the floor. Martin.
Thank you. Thank you. Ladies and gentlemen, it's a great pleasure to as well welcome you on our behalf. I'm Martin Albrecht, as the Vice Rector said. I'm formally chairing this division of organometallic chemistry. And why am I here? Because typically this division is formally commissioning the conference, the European Conference on Organometallic Chemistry. So we're kind of the board in the background that makes sure that these conferences take place. They typically take place every 2 years. And I have the privilege to chair that division together with Beatriz Royo, who is somewhere sitting here or maybe in the other lecture room as well. And she is originally from here, so it is quite nice that this somehow closes a bit of a cycle. These EuCOMC conferences, they take place every 2 years. The last edition should have happened 2021, and if I say should have, it's actually, it did happen, only it happened on a virtual space, and we all know why this has been. So it happened, so it was here organized to be in Alcalá, and then quite last minute, Marta and her team had to rearrange and get everything on a web platform, and we still had a quite successful meeting. But now being here, we of course know what we all have missed. We have missed the contacts, the bodies we can sit and talk to. We have missed this marvelous location. And even despite the rain, we are already enjoying, even though this has only started. So I'm very glad for Marta that she insisted to keep the conference not only in a virtual mode, but also to have it now 2 years later on site. She has been very successful in organizing this conference. As you all know, the lineup of speakers is something that we all look very, very much forward. And she has made with extremely hard work, she got together this marvelous conference that started seamless. The hard work started already months ago. We know because we had been in exchange between the division and the organizers. We know that the last months have been particularly intense, and the last days with the storm and people that cannot travel in on time or have to loop around. So this has surely added a bit of an extra taste to organizing this. And I'm sure this is not over yet. So while the conference is ongoing, there will be here a bug, there a bug. So rather than thanking her for the organization, which I probably should do then at the end of the conference, I'd like to provide her with some energy to also go for the last days to get everything going. Now energy in Switzerland, that's where I'm coming from originally, their energy has quite a long name, and it has the shape of a mountain. So I thought I'd bring her some you know, Swiss chocolate, so that whenever she needs some energy, she has some energy. So thank you very much for you and your team for organizing this, and I wish you all the success with this conference. Thank you.
Thanks a lot, Martin. I'm sure that Marta will share the chocolate with all. Now I'm going to give the floor to Professor Carmen Albeni, Head of the Organometallic Chemistry Division of the Spanish Royal Society of Chemistry. Carmen.
Thank you, Senor Vicerrector. On behalf of the Spanish organometallic community, I would like to welcome you to this 25th European Conference on Organometallic Chemistry. As Antonio has mentioned, organometallic chemistry has a long tradition in Spain, and we are very important. We have been, organometallic chemistry has been very important in the development of chemistry in this country. 42 years ago, exactly here at the same place in Alcalá, the specialized group of organometallic chemistry was founded inside the division framework of the Spanish Royal Society of Chemistry. So for us, this is a very special place and a very special occasion, and we are really proud to host this conference and having the opportunity to have here the main players of organometallic chemistry in Europe, and also to be the showcase of the exciting new developments in the area that have been doing all over the world. Organometallic chemistry is a purely interdisciplinary science, right? Along with the fundamental studies on the complexes with metal-carbon bonds and the new and unusual bonding and structural situations that we find, organometallic chemistry today aims to solve the problems that we are facing as far as energy, sustainability, and welfare of society. So, as Antonio put it, organometallic chemistry is very much present in the new developments in catalysis, in materials science, and in these other areas. So I'm sure that this will be shown here in this conference, thanks to all the participants. And thank you also to the great program that the organizing committee has put together for us. So thank you, Marta, and all the organizing team for all your effort. We have been in close contact this past year, so I am a privileged witness of their dedication, their enthusiasm, and their work, their efforts. So to all of you that are gathered here this week, I hope you make good use of this occasion to interact and to share good chemistry, and I do hope you enjoy this conference. Thank you.
Thank you, Carmen. Now I give the floor to Professor Martelena González, Chairman of the Organizing Committee of this 25th Conference on Organometallic Chemistry. Marta.
Thank you very much. And we are all very happy to welcome you to our beautiful city of Alcalá in this wonderful building where the historic University of Alcalá was founded in the 15th century. And first of all, I would like to thank all the people that has made it possible that today we can welcome you here, to all the speakers, and as well, because this is not just one person effort, obviously to the organizing committee that has been heavily involved in the whole organization and has been extremely helpful, and as well to the volunteers that you probably will be able to recognize them because they are wearing a green t-shirt with the logo of the conference. And obviously I would like to thank you all because I think the participants are the ones that really makes the conference to be successful through their enthusiasm and interest in the networking opportunities. So we are very happy to say that we have participants from any corner of Europe. An incredible number of European countries are represented, and as well from other parts of the world. We have participants from the US, from Japan, from India, Tunisia, South Africa, from Australia also, from Mexico, from Algeria. So all the continents apart from Antarctica are represented. We are nearly 400 people, And this is why today, although we can celebrate today the first session here in this beautiful building, then the rest of the conference, like tomorrow, Wednesday and Thursday, we will have to move to the campus where we have a bigger venue, and most of the conference will take place there in the campus. And the last day, we will be back here for the final session of this conference. To go to the campus is very well connected to the center of town, and you can use the local transport, but also we have organized a bus shuttle service between most of the hotels in Alcalá and the campus. All the info is in the webpage, and also is in the little booklet that we have put in your bag, so please check there all the info. And also there, and as well, you have any questions or any doubts, you can ask to any member of the organizing committee, and also to the volunteers that they are here to help. So I think I hope that you enjoy this conference. I think that we have an outstanding lineup of speakers, and as well a fantastic, a great number of oral contributions of excellent quality, together with fantastic poster contributions. We are, as mentioned before, there is a particular link of this university and organometallic chemistry, because it was here when the group started some years ago, and in fact the first president was Pascual Rollo, has already been mentioned, and the secretary was Victor Riera, and both of them have unfortunately left us in recent years. And Pascual Rollo was a professor here, and definitely the imprint that he gave about bringing the whole organometallic chemistry to the department and everything was very important. So on Thursday, we will be having a session dedicated to him. And as well, there will be a session to celebrate the anniversary of the Nobel Prize to Professor Wilkinson and Fisher for their pioneering work in organometallic chemistry. And in this session, Professor Werner, the winner of the first edition of the Fisher and Wilkinson Prize on Organometallic Chemistry, he will deliver a plenary lecture. And we have also another celebration in this conference, which is the 25th anniversary of the EuCOMC, the European Journal of Inorganic Chemistry journal. And then they have sponsored a young plenary talk on Tuesday, the one that will be given by Pep Cornellà. And as well, they will be sponsoring the cocktail, which initially, the cocktail at the end of the session today, that initially was going to be outdoors, but because of this unusual weather for this time of year here, probably has to be more indoors, but we'll see. And I must admit that we didn't expect all this rain, so hopefully at some point this week the weather will change. And then because we also have organized some other social aspects in the conference, like tomorrow there will be the visit to this historical building, and then on Wednesday there is an optional excursion either to a vineyard or an art gallery in Madrid, and then on Thursday will be the final conference dinner. So I hope that you enjoy this this conference, and it will be a great opportunity for you to do networking and to check what is the latest that is being done in this fascinating discipline that is the organometallic chemistry. And obviously I will share the okay. So thank you to you all.
Okay. Head of the Spanish Royal Society of Chemistry, Professor Echevarren. Chair of the EuCOMC Division of Organometallic Chemistry, Professor Albrecht. Head of the Organometallic Chemistry Division of the Spanish Royal Society of Chemistry, Professor Albeni, and Chairman of the Organizing Committee of this conference, Professor Marta. Dear colleagues, ladies, gentlemen participating in this event, good afternoon to all of you, and welcome to the University of Alcalá and to the 25th Conference on Organometallic Chemistry that, Martin said, fortunately is going to be celebrated in a presential mode in the city of Alcalá de Henares. After the last edition, that had to be organized in a virtual model, to have all of you here, about 400 people, as Marta said, is the best news that we could have. It's a great honor and pleasure for me to be able to participate in the opening session on this international meeting devoted to organometallic chemistry, not only as Vice President of Research and Transfer in this university, but as a chemist and particularly as an organometallic chemist. The University of Alcalá was one of the pioneers in the development of the organometallic chemistry in Spain, thanks to a group of researchers led by Professor Pascual Royo, to whom today I would like to make a special mention. Because Professor Royo created an organometallic school in our university, and since then, organometallic chemistry is the main area of research in our inorganic chemistry department and one of the main research areas in the University of Alcalá. And please let me tell you that I am very proud to be part of it. Some of those researchers that start their scientific career in organometallic chemistry in our university are the organizers of this meeting, and I would like to thank all of them, represented today here by Professor Marta Elena González, for the great effort that they have made to make possible the celebration of this international meeting. I know that all the people, including the youngest one, had collaborated to make possible the organization of the big event as this one. Thanks to the organizing committee for the big effort to keep the quality and the interest on this international conference. I think that you have gotten your objective and all participants will be happy with the program that you have elaborated. I really like the opportunity that has been given to young researchers to show their work in the field of organometallic chemistry. I am sure that all of you will enjoy the scientific program and will find a nice environment for scientific discussion. In the last edition, I regret that you could not enjoy visiting our university and our city, but this time you are going to have the opportunity to do it, and I hope that you like what we can offer to you. For the people out of Spain, it could be strange if I say that 1 week ago we have about 40 degrees and we didn't see the rain in the last 3 months. So the weather changed completely this week, but fortunately the forecast said that the rain should stop by now, and the weather should be nice enough to allow you to enjoy our university and our city. The University of Alcalá was founded by Cardinal Cisneros in 1499 with the idea of creating an authentic universitary city that will house the best professors and students in our country. That brought great figures of the Spanish culture to our university, such as Antonio de Nebrija, Tomás de Villanueva, Ignacio de Loyola, Francisco de Quevedo, and many others, and turned the University of Alcalá into an educational benchmark not only in Spain, but internationally. For this reason, UNESCO declared our university a World Heritage Site in 1998. The University of Alcalá is the only Spanish university declared with this distinction, and one of the only 5 universities in the world, together with the University of Virginia in the United States, Coimbra in Portugal, Caracas in Venezuela, and the University Autonomous of Mexico. This year, we are celebrating the 25th anniversary of this nomination, and what best that organized the 25th edition of this conference on organometallic chemistry. Today, the University of Alcalá is a modern university that looks to the future, but don't forget the past, and try to preserve our huge historic patrimony. Today, our university has about 30,000 students between graduate student, master student, and PhD, and about 2,000 professors and researchers that are distributed in 3 campuses. The historical campus that is in the city of Alcalá and where you are in these moments, the scientific and technological campus that is 6 or 7 kilometers south of the city and that you will know tomorrow, as Marta said, and we have a 3rd campus in the city of Guadalajara, 25 kilometers from here and that makes this university to be the only one established in 2 autonomous communities in Spain. Thanks for trusting Alcalá and giving us the opportunity to be closer and closer to all your institutions, programs, and projects. Once again, I reiterate my gratitude to the organizers of this Congress for the initiative and for their dedication so that everything be perfectly organized. And of course, I express my gratitude to all the participants in this event that are people from all over the world. With these words, I officially declare open the 25th Conference on Organometallic Chemistry. Thank you very much.
Is this off? Do we have to switch it off? It is. Okay. Okay. Ladies and gentlemen, this was the formal bit, and it's my privilege and pleasure to move on to the scientific program and to chair this very, very first session. And it gives me particular pleasure to introduce our first plenary speaker, Polly Arnold. Polly is probably known to everyone and every soul in this room, but then still it's giving me a privilege to give a quick background about Polly. Polly got educated in Oxford, and as an eyewitness said, mentioned just previously, she has been already very busy during her undergraduate work, then moved for a PhD to Sussex to work with Jeff Coates, and from there went for a postdoc across the ocean to go to Kit Cummins for 2 years and a bit, and then started her independent work at the University of Nottingham first for 7-8 years, and then moved from there to a chair position in Edinburgh, where at the end she was, well, not at the end, for quite a while, she was the Brown personal chair, or she had the personal chair. Before then, in 2020, she got an irresistible call to go to UC Berkeley and become the director of the Lawrence Berkeley National Laboratories. And that's where she has been since. In science, she has been very well known for all her groundbreaking work using F-block metals, both rare earth, actinides, making uranium, doing things that we never thought uranium could do. In other terms, she has as well been very active on an inclusion program, on making science accessible for really everyone. And so we have seen a lot of Polly, we have read a lot of Polly, and now we're very, very happy to hear a lot of Polly. So without further ado, I give the floor to you.
Thank you, Martin. And I put mine in.
Is this yours? Okay.
Oh, you're stopping it. Okay. Yeah, it's a great pleasure to come here, and for a Scottish woman to have some rain for the first time in months. It's lovely. Yeah, thank you for inviting me. Yeah, I hope it's a fantastic conference. I know it will be. I've seen the program. So. As Martin just said, we like to study the F block. And I just remind you quickly that the F block are also a transition metal series, right? They just transition through the F electrons rather than the D electrons. So we have to remember that if you say transition metals, you also may mean the F block. Okay. So There are many reasons why we would want to study them. They're actually very important in technology, and they are all around us. So you might have heard about them a lot recently as being critical materials. So the rare earths are used, the electrons in the F orbitals have wonderful properties for magnetic and optics. So they're the spices of technology. There's about 1 kilogram of rare earths in a Prius car in the magnets. And then, in fact, they're hugely used in the oil industry. So there's a very large amount of cerium catalysis being used in oil refining, which is maybe not the future of it, I hope. And then we also think of the isotopes being used in medical applications, and this is an increasing opportunity for both the lanthanides and the actinides being used for medical imaging and also for targeted neutron therapy on tumors, for example. We're also interested in the fact that we have these isolated F electrons and unusual electronic structures. People are beginning to find applications or potential applications in quantum information storage and also sensing at the quantum level where we can manipulate the isolated F electrons. And then we're also thinking about, for the metals at the bottom here, the actinides here, we want to understand how their bonding and behavior works because they are potentially useful for small modular reactors, small nuclear fuel sources, which can be fail-safe, safer for the future while we transition to a solar energy technology, I hope, a solar energy future. And also this suggestion that we may go beyond, having filled up the 7th row, there are still opportunities to understand new physics by pushing beyond. And who doesn't enjoy a bit of new physics? Huh? So if we think about the lanthanides in aqueous systems, where they're in the presence of air, most of them are 8 or 9 coordinate with water, isolated with their countercations floating around in solution. And this is why people have traditionally thought that they're very boring, because you don't have much control over them here. But if you can tame them, then you have this opportunity to move all the way across the lanthanide series to tune the size and the Lewis acidity until you get that perfect catalytic geometry, that perfect system. And also something that the D-transition metal chemists never talk about when they're trying to devise base metal catalysts that are moving away from the noble metals. If you want to make a catalyst that is environmentally friendly and sustainable, you think about making an iron catalyst. But iron is 6 times more toxic than cerium chloride by ingestion, right? So if you have good access and an environmentally friendly way of isolating your lanthanides, then they should be good catalysts and good catalyst materials if you can control them, which is where organometallic chemistry comes in. All right, so this is the abundance charts from the US Geological Survey, and you can see that many of them are equally as abundant as copper, which is also regarded as one of the base metal catalysts at the moment. And the US mined 43,000 tons of metric tons of rare earths last year. The problem is that we shipped them to China for reprocessing and then bought 80% of that material back for magnets. And this is because we have this problem of environmental damage done during the processing. And the reason it causes so much trouble is because we don't understand how they form bonds and how to differentiate them properly. So we need more chemical studies of them. Okay, so if we're thinking about better understanding them, it's also interesting where we do have these one electron redox properties, the same as with the 3D metals. So at the beginning and at the middle and near the end of the lanthanides, we approach the empty or full or half full shell. This is where we get one electron redox processes. And so we move away from so we can look for the 3-4 couple and then the 2-3 couple and get some interesting reactivity of these. But even beyond that, people using organometallic ligands are recognizing that if you get your ligand set right, you can actually make a formally +2 oxidation state for every single element of the 4F series now. And this is one of the molecules that's been most heavily studied, this type of molecule here, by Bill Evans. And this is 10 years old now. And this is where the electron sits in this symmetrical D1. And this does exhibit magnetic memory. So this could be a candidate for a qubit in a quantum computer. Right, and when we go down to the actinides, it gets even more interesting because by the time you are down in the 5F series, the energy of the D and the F orbitals is much more similar, which means you can start to make hybrids of both of these, which then enables you to have, thanks to relativistic effects, enables you to get access to every single oxidation state, right? Because, including uranium metal, right, which doesn't, of course, doesn't yet have an organometallic compound. But now we have these 5 different formal oxidation states that have been isolated with this one by Richard Layfield's group, most recently using these very rigid, sterically protecting isopropyl CP ligands. Right. And even here now we're starting to see development of electronic structure and ligand-controlled electronic structure that nobody predicted before. So this is very interesting to me and exciting, I think, to me. Here, this uranium-2, formerly uranium-2 compound, has a 6d0 with 4 5f electrons in its state, with a lot of electron density smeared out across the arene. And then this one, which I showed you the picture of the lanthanide analog, is a D1. So look at this. This is a ligand tuning the electronic structure of the metal configuration, which is exactly what we teach the undergraduates for the D block. And now the poor things are going to have lectures on ligand field theory with 7 F orbitals in it. So I'm glad I'm not an undergraduate anymore. And if there are project students in the audience, good luck, you made it just in time. Okay, so we've already mentioned ferrocene, of course, as you should. This is always the first sentence in an organometallic conference. Just a reminder to everybody that these sorts of organometallic sandwiches have given us a fantastic education in how we order the d orbitals and where we put the electrons. And these pi cyclical ligands, first for ferrocene and then for chromocene, which is chromium 0, gave us this understanding of how to match and use the symmetrical combination of the p orbitals, the pz orbitals in each of these carbons available in these systems. And so that's the structure that takes us to 18 valence electrons for a d block that we all know very well. And these are the bonds, the orbitals that are doing the bulk of the interaction here, that's giving us opportunities to understand this electron overlap between the d orbitals. And so potentially this is how we then want to move on and think about going to f orbital overlap. Right, and this is, to do this, Streitweiser and Müller-Westerhoff decided to progress to this dianionic ligand when they moved down to uranium. So now we can get to a higher symmetry for uranium compound, and they isolated this. So this is the version of ferrocene or chromocene for uranium, and it's in the +4 oxidation state. And you can see that you can divide these symmetrical orbitals and get to the phi overlap, which is mostly with the 6d antibonding electrons in uranium. And this has been very widely studied as a result of this opportunity to use all of these different orbitals in the bonding with the metal to different overlap. And then I just want to go back and briefly mention work that Jeff Cloak did that was really pioneering in this field in the 80s, where using metal atoms as a source of zero-valent metal starting material, and it's still the only source for a lanthanide of zero-valent starting material. If you evaporate metal inside an evacuated bell jar, and you cool the walls of the bell jar, and you add in some ligand at the same time, something volatile, you make a slushy in the liquid nitrogen-cooled wall, and if everything and all the orbital overlaps will align well, you can isolate these formerly zero oxidation state lanthanide complexes. So you can only make them from metal 0 at this point in time. And there's so much, there's a little bit of donation from the arene to the ligand, but there's a huge amount of electron donation from the lanthanide back to the arene pi star, showing this mixtures of orbitals. And so really you can think of them as more like a lanthanide +2. But again, these can be made for almost all of the lanthanide series. But they're incredibly air sensitive. Right. So we were very interested in these calculations that Dolg had made 20 years ago, suggesting that benzene should be an excellent ligand for uranium, so just the simpler version, and as a neutral one. And we can imagine how getting to low formal oxidation states of uranium would be interesting in this way. But the problem is, you can't evaporate uranium in this system. You can try from a uranium-rhenium alloy, but it's not really ideal. Right? So we saw this ligand, and we were encouraged to use this, having read Gambarotta's work on samarium compounds here. So this is a dianionic, a small macrocycle, and it has these two acidic NH groups here that can make this formally a 2- ligand, so you don't need to rely on all of the charge getting to your lanthanide. So we can hope that we can start to explore the electronic structure of an actinide overlap using this ligand here with the arenes binding nicely. All right. So we take the lithium salt, the dianionic form of this ligand, and we add uranium triiodide, and we do this in the absence of donor solvent so that the only thing remaining to bind to the metal is the arene, and we make this macrocyclic uranium compound here, where the equatorial plane has the 2 pyrrolide anions, and then the X ligand, which is iodide here, and then we see this bis-benzene structure. So we're cheating, but we get the structure that we were looking for. And if you look in the crystal structure of this, you can see that the uranium centroid distance is 2.6, I can't read it, 2.669, which if you subtract the radius of uranium is actually shorter than the samarium centroid distance here. So already we have a better overlap between the uranium and the arene. What's interesting for us was that if we changed the geometry, the stoichiometry, we put 2 equivalents of uranium-3 in here, still working in an arene solvent, we can actually get 2 in. So this was pleasing because now we can compare the arene binding to uranium with the equivalent of the CP binding to uranium here in exactly the same system. These metals are also incredibly close to each other, and they look like they should be electronically coupled, but the magnetism is very boring of this compound, so I won't show you. Right. Instead, what we can do is collaborate with Nick Kaltsayanis at the University of Manchester and look at this metal arene and metal equivalent of a CP overlap in the same system here. So the first thing that I want to point out, I put these in the wrong order, didn't I? So there's 7% of uranium-6D arene pi symmetry overlap from the uranium here with the benzene in this system here, right? So that doesn't sound like very much, but if you look at the analog, the simple analog of tungsten bisbenzene, that's actually only 15%, which is a smaller number than I would have expected until Nick ran those calculations for comparison. So this isn't bad. This is pretty strong bonding, but in fact, it's about the same as the amount of 6D pyrrolide pi interaction with the other uranium here, the second one in the back. And that's because the pyrrolide is more, it has an anionic charge on it already, so you're increasing your propensity to overlap. But between both of these, this is giving a significant energy to stabilizing the system. And it has to, because there's actually quite a bit of strain in this bimetallic structure. So you need that covalent bonding interaction to give enough stability to isolate this compound here. All right, and of course, now we want to do transuranic chemistry with it. So we went to our friends in Germany at the EU Joint Research Facility in Karlsruhe, and there we work in glove boxes which are designed to protect the person and not the compound. And so you set up a Schlenk line inside your glove box, and if you wear a red band if you're a visitor. We have all these amazing facilities, many glove boxes, a great capability to do research. But the most accessible starting material they have there is the neptunium-4 chloride. So you'll see the stoichiometry is a bit funny in this reaction. This is optimized, because when we do this reaction in THF, we get the salt elimination the same way as we were seeing with the uranium analog, but now we make the neptunium-3 compound. So this is actually good for us, because this is showing us that the lower formal oxidation state is preferring to form these covalent interactions with the arene, and it spits out some ligand decomposition products in order to give the more stable, more favored oxidation state of neptunium-3 in this system. And luckily for us, we also get the same structure. So, sorry, that used to be rotating. Not that you needed to. Yeah, so now looking at this, we have to compare the chloride with the iodide from the structures we have before, but hopefully that's not too important. So what we now notice is that the neptunium centroid distance is even shorter than, after comparing for ionic radii, it's even shorter than it was in the uranium system. So we're increasing the overlap as we go from samarium to uranium to neptunium here, which is good. So neptunium is thousands of times more radioactive than uranium, which we already have to do a lot of paperwork before we work with. So it's nice to be able to do this, but we don't have much access, and we have to be very careful the way we do this. So we don't get many goes at doing these reactions. So it's nice to be able to work with Nick Kaltsianis again and think about what the electronic structure of these systems look like. Because in the computer, Nick can compare the samarium compound with the uranium compound and the neptunium analog. And he makes the iodide in the computer for each of these. So the first thing you notice, of course, is that as you go from the 4F to the 5Fs, the red lines indicate the F electron system, and we get this dramatic increase in energy to the uranium 5F3 here, and then dropping down, as you would expect as you go across the series. It's going to taper down in energy as we go across. And then the next thing that we notice is that the metal-arene bonding here is in these colors here, the blues and the pinks. We're finding that there's a pretty good 7% or so interaction between the arenes and the metal in each of the cases, and actually not hugely different between them. But the other thing, of course, we have to remember is that covalency can be demonstrated in any of the metal ligand bonds. So when we're designing a multiple ligand system, we mustn't just only think about the complicated ligand that we designed. We can also see it in the simple parts of the system. So in fact, the contribution from the iodides to orbitals, the sigma and the pi orbitals, is changing hugely. So these 10% and 2% numbers are up to 19 and 17% in the covalent interaction that the neptunium iodide is making in this calculation. And so here are some of the pictures of this orbital. And in fact, it's easy to see that the F electrons on samarium and then the iodide orbitals are really not showing much interaction at all, but there's significant orbital overlap-driven covalency in this system here. So that was really very pleasing to see. And it's nice to see that it was worth studying neptunium after all of that work we went into making it as well. Right, so there we go. More ionic and more covalent is the summary we get. So we need to find a better system, right? We need to get rid of the halides, and we need to find something that is purely organometallic at this point. All right. So first thing we do to try and get rid of the halides is reduce it. We were hoping that this would be sterically protected enough that when we eliminate the chloride, we could just make the bisbenzene type neptunium compound here. So even though we're working in a radiological facility, we have to keep quite quiet about this. This is a NaC reacted in alongside a radioactive metal, but when your red solution, your red compound, goes to a beautiful blackish color, greeny black color, when you add the NaC to this. And we believe that this is the compound we're isolating. We know it's chloride-free. We have UV-vis spectra that coordinate with what we would expect from adding this one extra electron into the system. But the problem is it's not very stable. So if we keep a little bit of NaC in the bottom of the flask, I know you shouldn't, right? But don't tell anyone. But we can see that when the compound warms up, and it only lasts for a few hours, if we keep the NaC there, it reforms the low oxidation state compound. So that is in line with the fact that the decomposition product that we're making is breaking the DME, it's cleaving a methoxide from the DME, and the neptunium has lost its halide, but is getting a neptunium methoxide instead. So clearly this ligand didn't have enough steric protection to isolate this, what would have been the first neptunium-2 compound in here. Right. So we don't really want to do chemistry with NaC in the bottom of it, so we left that. And this was a very nice structure, and you can see that the ligand is rearranged to form something more like the CP, in line with what we were expecting to be the stronger pi overlap and delta overlap in the system, the pi overlap anyway. But it's also methylated the ligand, so we need a better ligand than this. All right. And the other thing we tried to do is see if we could make the equivalent where we had 2 uraniums in the system here. But as I said, we don't have much access to this material. So when we add the stoichiometry that would give us 2 neptuniums in 1 ligand, we do make a compound that contains 2 neptuniums, but we're doing this reactivity in THF, which is a good donor ligand, of course, for neptunium. And so the crystals that we isolate are beautiful, but they're neptunium 3 with chlorides. So we've still done the ligand reduction, but we just can't get rid of those THFs in the radiological facility to make what we hoped would be the neptunium compound. So one thing I didn't mention was that this molecule, again, when you cool this down in the squid magnetometer, we see a slowing of the barrier to magnetic relaxation. So this molecule is heading towards being a single molecule magnet, but we don't believe that that's particularly useful or important, so we stopped looking at that bit there. Okay, and then, yeah, the moment happened, the word that you can't say in Scotland happened, and I had this opportunity to move. So I trended on Twitter as Pexit for a while, but I was beaten when Meghan and Prince Harry left because Mexit took over, but you know, that's fine. I don't want to be famous like that, that's okay. All right, so I Pexited, and I came to these beautiful halls and spires. This is not any of the photos of the labs, of course, because our labs are leaky and stuff, but they're old, but they're very good. But then up here in the National Lab, where we have these wonderful views out across the bay to San Francisco, and we have this giant synchrotron in the middle of everything. We have fantastic equipment and amazing people, and all the way across the campus and across the National Lab, which are 10 minutes away from each other. We have fantastic ability to do things. And in particular, unlike Brits trying to get access to an EU joint research facility, we have our own research lab for doing isotope chemistry. So we have the HURL, which is unique in its ability that there we can handle any isotope that we can get our hands on from across the periodic table, right? So we have, with power comes responsibility, of course, right? So when I moved there, we spent a lot of money, or a lot of Americans' money. Thank you for your taxes, America. Don't worry, I pay them now. Some big double glove boxes here. You can see that the gloves are tied together because they're under negative pressure because we're protecting the worker. So we have this counter activity of you have to protect your compound, but then you also have to protect your worker. So we're pushing either argon or nitrogen through these boxes at a great rate, and so that the person can wear them, can survive, and wearing a mask here, can handle these transuranic elements. We bring the samples in one at a time. We store them somewhere else so that you don't get exposure to them. And then we bring them in one at a time. And we clean the glove boxes in between each time. So we don't store stuff in them. We have a lot of spectrometers inside them. And then the spectrometers that are too big, like the X-ray diffraction, single crystal X-ray diffractometer and the NMR machine, we just have to doubly contain all our samples so we can paint the surface, or we put them inside a Teflon tube, and then we can carry them to the samples. So there's a lot more paperwork to do, but the opportunity to work with all these isotopes is really wonderful. Right. And so this now means that we can go beyond neptunium, the first non-naturally occurring element, to everything that is beyond uranium. So all of these transuranics, right, we now potentially have access to if we can get them from a supply, right? Because you can't just buy them on Aldrich, thankfully. So this is the sum of the organometallic chemistry that is known for beyond plutonium, right, pretty much. So these tris-CP compounds that were first made in the 60s and 70s, so pretty much soon after Seaborg was isolating these things. And we have these minute quantities of they were made, because they were made from molten beryllium bis CP, which is in itself a pretty challenging molecule to work with. So most of these are characterized by what we would call optical spectroscopy, right? So this is a beautiful color. That's pretty much it. So, right. And so the thing that made us particularly interested in studying some of these is that we have this increasingly unusual range of oxidation states that have been suggested. So small-scale tracer experiments, particularly with berkelium in this case, suggested that of the transuranics, berkelium is the one that should be most easily accessible in the +4 oxidation state. And so if you think about the lanthanides, the cerium, the 5F1, is very stable in the +4 oxidation state. So down here is increasingly +4, and up here is increasingly stable +3. And so we were particularly interested in berkelium, wondering whether we could use this to think about getting to this bis-cot, the berkelsine type sandwich compound. And then we could explore its relevance to cerium and how it might work. So there we go. Those two, the cerium and berkelium. And they're also interesting for the future is look how stable these later transuranics are. So these ones also should be stable in the +2 oxidation state as well. So there's a lot more to do in this field. Right. So we got very excited about trying to think about making berkelium organometallics and thinking that COT2-, the cyclooctatetraenol anion, would give us this opportunity because it has this high symmetry and this ability to make these multiple overlaps. So this is a picture that comes from Streitweiser's paper when he first reported uranocene. And you can see he's highlighting the fact that in addition to the pi, we also have the phi. So we can get delta and phi interactions with all of these metals. So 2 COT ligands should allow us access to S, P, D, and F symmetry overlaps in these systems. And it's interesting as well to compare berkelium with cerium because cerium should be traditionally the +4 organometallic, but cerium-4 is of course a very strongly oxidizing ligand. And so you would think that if you try to make a cerium alkyl compound has never been isolated. And so the classical picture of perfect +4 and perfect 2- ligands is not really actually very accurate, which is interesting. So in the 70s, cerosine was uncontroversial. And people made it and they just went, okay, this is great, +4, 2-, right? And it looked diamagnetic and it seemed to be okay. And it looked like thoracine, which is right at the beginning of the actinides, D0, F0. And they thought it would be fine. But of course, at that time in the 70s, a lot of things were uncontroversial, right? That maybe nowadays we know a little bit more. This is the picture phone made by AT&T. And I've never seen one of these, but yeah, anyway. Yeah, be thankful that's not in your pocket right now. Okay, and so then this big fight started, right? So in 1989, people started to do calculations, and they said, okay, actually, this looks more like cerium-3 with a 4F1. And then the COT is reduced, right? So it's not really very much like a -2, it's more like a -1.5. And they saw temperature-independent paramagnetism, and so things start to look strange in this. And then people started to do increasingly complicated calculations, right? And then as time went on, people continued to try increasingly advanced X-ray spectroscopy techniques, variable temperature, magnetics, and more at the synchrotron. And then in the end, everybody decided that it's a mixed configuration. It has a multi-configurational ground state. So there's a fraction of cerium-3 and a fraction of cerium-4 superimposed in the same element at the same time. Right? And then this is one of my favorite quotes from a computational chemist ever. Right? Matter of taste and perspective. Right? So I don't know how many papers you then get to write after that. Right? And so because of all of this, during all of this time, people have now made the sandwich molecules with COT for everything up to plutonium. So that's up to uranium, neptunium, plutonium. Right? So we wanted to do berkelium. Right? So we don't care about curium here, or americium. We just went straight for berkelium because of this possibility of getting to the +4 oxidation state I mentioned. But it's very difficult to get hold of. Right? So 10 milligrams once every couple of years. And once you've got it, it has a half-life of 330 days. Right? So the moment you get it, it's starting to decompose into californium, which is okay if you want to do californium chemistry, but also californium is significantly more radioactive, so we really don't want it to be decomposing. And californium doesn't have a potential of a +4 oxidation state, right? And of course, californium is an alpha emitter, so it's increasingly, so we should be able to stop it. But anyway, so we ask the Department of Energy if we can have some berkelium, and then Oak Ridge National Lab takes a curium target and they place it in the bottom of the nuclear reactor they have, and they bombard it with neutrons, and you get a lot of elements out at the same time. They then take it into a hot cell and they separate out all of the individual isotopes from this through columns, everything working with remote controls. And then this is what we got sent 18 months ago. So this is 0.5 milligram in the bottom there. Maybe you can see it, it's slightly yellowish, right? 0.5 milligram of berkelium, and it's already beginning to convert into californium as well. So we were extremely excited by this point. And we'd been planning for ages, right? We knew it was coming, we knew we'd asked for it. So we spent months doing the chemistry that we planned to do with 0.5 milligram of berkelium, planning with cerium, right? So we have cerium, this dubious +3 +4, and then berkelium, which we're hoping will be really significantly +4, right? So cerium is about the same size, and it should give us a pretty good surrogate, a pretty good chance to practice. So we scale down all of our syntheses of all of these different cerium functionalized cyclooctatetraenol complexes, hoping that we'll be able to get something that we can characterize before the californium grows in enough to confuse the characterization, assuming we can make it. So we have a very alkylated one, we have a normal, a vanilla cot, we call it, and then we have these very bulky silylated cots here that are weaker electron donors, but also give us another handle for X-ray spectroscopy, because we can look at the silicon edge, absorption edge in X-ray spectroscopy. Right. Okay, so do you know about this, how to understand? You've all done organometallic transuranic chemistry before? Worried about this? No. Okay, so you can, this is just a silly joke slide to wake you up halfway through. You can work out your exposure from banana equivalent dose. This is on the internet to help you understand how much of a dose you're getting from all of your stuff in the environment, because of course bananas have radioactive potassium in them. And I love this scale because it helps us remain sensible while we do our transuranic synthesis, right? So this is how much exposure you get from rocks. That's quite a lot of bananas, quite a lot of banana dose. You get a bit from X-rays, a little bit from food. You get a lot from coal mining because radioisotopes are released during coal mining. And then you get almost nothing from the nuclear fuel cycle, which is the advert, of course, that comes from the nuclear fuel cycle, but also very little from Chernobyl, unless you're eating wild boar. So this is good. Brazil nuts always worry me because they have radium, and radium is not going to be cleared by your body. And then this is also an amusing one because this is cumulative, okay? So the more people you add, yeah? So watch out for that. Yeah, okay, so back to the science. This is our practice run, right, that we've been doing for months in a normal glove box. So this is 0.5 milligram of cerium-3 chloride, and we evaporate it and we dissolve it in DME, and we add an excess of all these reagents. And then we have to find conditions and the salt elimination chemistry that we're going to get to work, and then the oxidation chemistry that we're planning on getting from cerium-3 as the 8 complex up to cerium-4 as the neutral cerosine plus 4 cerosine. And all of these reagents have to be compatible because we only have 0.5 milligram in here. And so we're going to have a little bit of, we can evaporate reagents in the middle, but we're going to have a bit of lithium sulfur cot left over. So that's going to be consumed by a bit of this. So we need a bit of an excess of this trityl chloride in here as well. And then the byproducts from the trityl oxidation are going to remain in solution. And then we have to crystallize our compound in under 3 hours, which is why we have so many different cots, to see if we can grow single crystals so we can get diffraction. Right? And then here's the berkelium chemistry. Once we think we've got it, by the time we got it sorted, there's a bit of californium in here, so we're actually working with only 0.3 mgs of berkelium. We're going through this and we can see this pale yellow and it's all looking very good. This looks nice. And then we make this rather lovely orangey yellow berkelium-3 compound. But we don't have time to characterize this. We've got time to get a UV vis, but straight away we go on and we add the oxidant and we get this berkelium-4 compound. So this was very pleasing because the color change is phenomenal. You go to this very strong, dark, purpley blue, right? And it's very different. So the cerium is strongly purpley as well, but it absorbs in a different part of the UV vis spectrum to the berkelium here. So it's very clear that characteristically giving us this ligand metal charge transfer here from the delta to the phi orbitals on berkelium, and really very pleasing. And then we have, I think you can see in the photo, can you see the single crystals growing here? Which is exactly what we are hoping for. The other thing I need to point out is that we have done this for the vanilla cot, but it's worked best for this HDC cot. So we have these alkylated groups on here, which is also helping us stabilize the +4 oxidation state. And oh, sorry, I should have shown that photo. That was what happens when we dry it down to the berkelium chloride. So this is the first crystal structure of a berkelium 4 organometallic. And so we can look at the distances. We don't have a very good idea of what the ionic radius of berkelium we should be working with is here, but we're pretty happy with this as the +4 oxidation state. The other thing we notice is that the HDC ligands are rotated past each other a bit. And they're kind of folding over as though to protect the metal. Well, we're not quite sure if that's significant, this folding yet. All right. I think you can see it if I rotate it, the rotation around there. Yeah. Okay. So it's nice to then go back, of course, and compare it with the cerium structure, where we're much more confident about the formal oxidation state and the bond distances here, and remembering that berkelium and cerium berkelium is ever so slightly smaller, we think, than cerium, and it has this 5F7 configuration here. Right. Right. And so we've also done calculations because we were concerned about whether the rotation is different. So notice, I should mention first, the rings are staggered with respect to each other, whereas in ceracine, they were parallel with each other. Right. So because of the slightly larger radius, it could be that that is the preferred orientation, and there's just not enough rim with berkelium. But the calculations that Jochen Auersbach does for us at SUNY Buffalo say that it's actually not a problem, right? So he can measure the energy of the molecule as he twists the rings with respect to each other, and you can see a point where it becomes unfeasible, but in fact there's essentially no difference in energy between these two. So we're confident that that's a crystal packing effect within the crystal. So we're pretty happy with that. I'm very pleased to confirm that it is berkelium 4. But even better, Jochen can also do these calculations for us, right? These are difficult calculations. They're using the complete active space, and we're looking at 15 electrons and 13 orbitals for this berkelsine compound. And he's also done the calculations for the COT, the vanilla COT, the normal COT compound, and then for the HDC COT complex here. So with the alkyl groups on this, right? First of all, you can see that we've got 7 electrons, 7 F electrons on the metal to contend with. So we have to run a lot of different spin states thinking about this. But using a localized basis set, what he finds is that the berkelium 4 contribution is 70%. So reminding you, here is the cerium calculation for the same COT, the HDC COT, where you see a multi-configurational ground state of predominantly cerium 3. See here, mostly cerium 3 with a 4F1, and then 24% or so of cerium 4 here, the F0. But when we get to the berkelium, we're seeing much, much less of the berkelium 3 in the multi-configuration and 70% of the berkelium 4 in the system. So the covalency here is dominated, as you can see. These are all the different orbital overlaps that they find. And then this one, this delta symmetry, is actually the dominating structure in here. And we get much more ligand to metal bonding to cerium than we do to berkelium. So this is looking much more like berkelium 4, which makes sense if you think about it, because berkelium has this 7 F electrons in its shell, right? So it would make sense that you don't want to put any more extra electron density onto the metal, and you're better off leaving it as more like berkelium 4 and keeping the electrons on the ligands, right? Whereas with cerium, it's only got 1 F electron, and so it's much easier, if it's cerium 3, and if it's cerium 4, it has nothing, so it's much easier for the ligands to donate electron density back in, and so you get much more of a smearing out of the electron density across that way. So again, when we talk about formal oxidation state, all of these things are really important. that we remember that they're formal. And if you want to draw Lewis structures, I'm very happy to keep on writing sericine as cerium-4, and thinking about when it does reaction chemistry, it will lose that COT2- ligand. But if you're thinking about electronic structure and spectroscopy, I would think about it as cerium-3. Whereas for this, both of these chemistries, both electronically and reaction-wise, I would think of berkelium as being +4. So this is really great to have been able to isolate this formal new oxidation state for berkelium. All right, and then the other final calculations I'm going to show you are from Jochen Auschwitz group again, from his postdoc Dimitriou, who has done these CAS-SCF calculations for all of these actinides here. So we've gone from both for cerium here, where I'm reminding you 20% cerium +4, all the way through the actinides, going through. You can see there was no point doing these, right? But it was well worth studying berkelium because we get so much of a +4 formal oxidation state. And the other thing that I'd be happy to talk about afterwards is that thorium, which is, of course, D0 right at the beginning of the series, you would always think of thorium as being rigidly +4, very difficult to reduce. But in fact, berkelium looks more like +4 than the thorium in the system, which I think is surprising and interesting. And we're still talking about this with Jochen all the time. So the 5F7 formal oxidation state, the closed half shell, is dominating for berkelium, which, if you think about it, is a bit like europium-2, which is the most stable lanthanide +2 with that half-full shell. So there we go. So I'll finish off by showing you 2 photos. This is the view from our new labs. So come and visit. Now everyone's allowed to travel again. Come and visit. Yeah, this is looking out. This is actually where people smoke. But other than that, we're in a high fire risk zone. We only smoke in one place. That's the Golden Gate Bridge. And this is the Bay Bridge off to San Francisco. And down here is campus. This is one marina where we go sailing and kayaking. And this is another marina where we go sailing and kayaking. And then we can swim. Anyway, you can, etc. Right, and then this is the view east, and this is even better, right? So this is the advanced light source, where we can do soft and tender X-ray absorption spectroscopies and some of the hard metal edge spectroscopies for the lanthanides. So we're poised now to start getting X-ray spectroscopies of understanding where the electrons are in all these systems. And this is accessible through a user proposal to anyone around the world. So it's paid for by the DOE, but you don't have to be an American to use it. So if you wanted to come and do some spectroscopies on your compounds, then just sign up. Just look on the ALS website and sign up, try and get some time, because it's really, really great facilities for doing science there. All right, so I hope I've shown you a whole range of interactions of pi systems with actinides. So I've shown you some 5-membered rings, although they're a bit negative, so it's not so exciting. 6-membered rings, and then some neptunium, and then finishing off with berkelium. So we have all of these different access through different organometallic ligands to all of the different possible symmetries of overlap, and it's teaching us so much about covalency and bonding in these metals and allowing us to get to oxidation states that are just not possible with simple coordination chemistry. And so organometallics has got an awful lot more to help us with in the future. I'm speaking to the converted when I say that. And so these are some of the, I'm sorry, that's not very well. Yeah, it's Michaela and David and some lots of other people from my group and from the collaborations within the Heavy Element Research Lab. So we share that lab with our colleagues in the Heavy Element Chemistry group. And these are the people who first came out to Berkeley with me. So that's very cool. And they've all gone on to a fellowship at Idaho and working in Bonn as a postdoc and various other things. So I'm particularly grateful to them, to Nick and Amy, who did the bulk of the Berkeleyan work in particular. Amy's just starting at St. Andrews as well. Nick is going to be staying with me for many more years, and we're gearing up for our next delivery of Berkeleyan. So thanks very much to them, to Nick for calculations, Jason collaboration on the neptunium, the uranium systems here, the heavy element people I mentioned. Thank you so much as well to these people for funding, and thank you so much for your attention.
Thanks very much, Polly. What a wonderful, wonderful start of this conference. We have time for a few questions, so I'm sure You happy to answer? Or what's this?
Let's talk about the future. So very nice talk. And you look at the decay of berkelium to californium. So actually, because probably if you have a single crystal, you should be able to see the change. If it doesn't change symmetry, you should be able to look at that by X-ray. Have you started to look at the berkelium to californium?
So what I forgot to mention in my consideration of time is that when we do the oxidation step, we actually get isotope separation, right? Because the californium precipitates out. So this is also a very rare example where we can get very pure data on just berkelium-3, because anytime anyone in the past has done coordination chemistry, they're always looking at a mixture of californium and berkelium at the same time. Does that answer your question? I don't think it does.
No, but do you see the decay? Can you actually see? When you have a pure compound, can you actually see?
You can see it in the crystals. When they're sitting under the oil and you're fishing them out,
yes.
You can see the crystals blow themselves apart. One decay happens, and there's so much energy comes out from the beta decay. Yeah. So you just get a powder, which you can put on the diffractometer because there was only one decay that killed the whole crystal. And that's why you need things to go so fast, because your crystals would just not last. Right? So the first crystal you try is the only crystal you have a chance for trying. So my students are really good.
And you think you can do X-ray absorption spectroscopy, so to go to synchrotron and to do millisecond time scale and look at the decay in the synchrotron at low temperature?
So we'll be able to see the californium growing in, but it won't be the compounds we want. I can't imagine it holding the ligands at that point. So we're better off looking at other systems for that. Or retaining the +3 oxidation state and looking at them just as a mixture before that happens,
Thank you.
The first synthesis of an organometallic neptunium compound was actually made by taking a uranium compound and bombarding it with neutrons until it became a neptunium compound. So these things are possible, but nobody would do it that way now. Not offending you, question. Yeah, so the question was, did we carefully select our ligands so that we could grow crystals as quick as possible? And the answer is yes. That's why I showed you so many of the COT systems. And the supplementary information for that manuscript was going to be very big, and then we realized we could write an entire manuscript separately on all of the slightly harder to crystallize cerium compounds, which has given us beautiful spectroscopic insight. But yes, it was a lot of work choosing. We spent a lot of time talking about diisopropyl because that gives good, but there's a risk of disorder as well. And given that we weren't sure that we knew enough about berkelium, we really wanted to get a crystal that was not going to have any disorder in it as well, so that we could be confident.
This is a question about the characterization, because basically you need to use X-ray spectroscopy to characterize the compounds to see the evolution of the reaction, or can you use more normal type of spectroscopy? So we do have NMR spectra of the compound, which was hard to get, and it doesn't really help. If you try to get the NMR spectrum of the F7 gadolinium compound, it's broad and paramagnetically shifted, and you really can't see very much. And it was the same with this. So we do have NMR, but they're pretty nasty. The first thing we always go to is UV-Vis near IR, because as you get into the near IR, you can see the FF and the FD transitions, right? And those are characteristic, and those are things that we've known about for many years, right? So we use those. We spend a lot of time thinking about those. But growing a single crystal and getting the structure is, it's the thing that we all really want in the end, isn't it? To have the picture. Yeah. And electron diffraction instead of X-ray diffraction is working for these compounds? That's a great question. So we're next to the National Center for Electron Microscopy.
and they have the ability to do microelectron diffraction, and they're working on 4D STEM, which is an opportunity to, with really good mathematics, you can take a grid, a TEM grid, and you smear just a powder across the surface, and it can even identify different phases, but it will collect diffraction data. It tilts the grid as it goes, and it will collect diffraction data on every single crystal, and then do the maths to solve it, and you get a structure. But this is too radioactive for us to be able to get to NSEM yet, but we have a project going, so by the end of the year, we may be able to get we'll never have to grow crystals ever again. We'll just take what we make and put it in there. And so hopefully that's the future. Yeah.
Okay, thank you.
Any last chance for a question here? If not, there's not the last chance, because there will be, I think, a reception, and Polly will be there, and she'll be, I'm sure, happy to answer any questions there as well. So, thank you again for a wonderful start of the conference. Okay, as we do the technicality changes, I have the pleasure to introduce our next speaker. That's, you have your presentation now. Mónica Pérez Temprano will present her work. Mónica has been born and raised in Valladolid, not too far from here. But then, so there she did her undergraduate, also her PhD with Juan Casares and Pablo Espinet, and then moved to Ann Arbor to work with Melanie Sanford as a postdoc for 3-4 years. And from there jumped back to Spain and got first a junior position at ICIQ, where she is now moving up the ranks. She has been there on a very successful program, moving to first row transition metals, so transition metals without much F electrodes, but their own peculiarities and perks. And we look very much forward to your presentation. Thank you.
Thanks, Martin. I would like to start thanking Marta and all the organizers for this opportunity. I was sitting there and I was thinking that I have mixed feelings, because I think that is great pleasure to close this session, but it's kind of unfair to go after Polly. It's really unfair, because you were completely amazing. So I will try my best to just keep the bar high. So today I will show you part of our work on mechanistic studies, and I always like to start my presentation with a little bit provocative statement. So pretty much we are synthetic organometallic chemists. Most of the reactions that we set up in the lab fails, especially for the youngest. Don't worry, it's like that. So you are doing a good job. When we think about failed reaction, we can think about the reaction where the starting material are not consumed, or we see byproduct formation, or when the starting material is consumed but we don't see the product. That, from a mechanistic perspective, that is very interesting to me. But from a synthetic point of view, we can have also low-yielding reaction or reactions that work under harsh reaction conditions, and this is the starting point for the optimization process. So we start trying to get the best reaction condition, and then we try to develop a scope, and when we are happy as an author, as a researcher, we want to share our result with the community, but we only share the reaction that work. And that is a huge problem, not only because we are putting into the trust pretty much more than 90% of the thing that we do, is also thinking in the new era about artificial intelligence. Right now, our literature is completely biased toward a positive result, which is a huge problem. But not only that, when we think that our reactions are robust enough, we see something like that. So in 2015, Merck disclosed a fantastic paper investigating the Bagwell-Harvey combination, and all of you will agree that is one of the most robust transformations that you can find, and is daily basis used in industry. And when they try to translate this reactivity to drug-type molecules, they discovered that more than 50% of the reaction that they tried didn't work. This is kind of scary. But even worse, in 2016, Nature put together a survey, and the 80% of the chemists that respond recognize that they cannot reproduce other people's work. So if you put together this is kind of a very frightening scenario. And this was a little bit the starting point of my group. So basically, there are for me two big questions. Why do reactions fail, and how can we capitalize on those failed reactions to streamline process design? And the answer for me, at least, or from my group, is something very simple. At the end of the day, the successful or failure of any chemical transformation, in our case we work with transition metal, relies in the performance of the intermediate involved in the elementary step of a catalytic cycle. This may seem very obvious, but normally is overlooked, and this can be a completely game changer for not efficient transformation. So what we do in my group is to use mechanism as a priori tool for reaction design, and what we want to do is to trap this reaction intermediate and use them, we call them knowledge building block, to overcome limitation and to explore innovative reactivities. So basically, this is our way of thinking. So we use this intermediate to identify a problem, we propose a solution, we test the solution. If it doesn't work, we come back to the square one. But what we want is to improve efficiency and create new reactivities. So basically, we want to use lean management tool for chemical design, putting the understanding at the beginning of the whole process design and development. So we have two main research lines. In one, we explore the role of Konitz methyl in organic synthesis. So Pedro Perez, sadly, he's not here because he couldn't come because of the rain. But I still remember when I was an undergrad student, and he gave a talk in Valladolid, and he said that it's very curious when you have a reaction with an arrow and with a bunch of things above the arrow, a bunch of things below the arrow, and you remove the Konitz methyl salt and the reaction doesn't work. But those things never appear in a catalytic cycle. So those inorganic salt that we use in daily basis, they are way more important than what in principle we can think, and we are really interested in those transformations. But today I will share with you our travel on cobalt catalysis. And this is particularly interesting because I told you that we want to use mechanism as a tool for developing new transformation. But what happens if you don't have any fundamental mechanistic knowledge to start with? That was our point in 2016 when we started this project. So I'm sure that I don't have to convince you that CH functionalization is the ideal method, one of the holy grails in synthetic organic chemistry to create carbon-carbon and carbon and heteroatom bonds. Indeed, in 2021, Chemical Engineering News put together a fantastic overview of this transformation, as you can see here, how the exponential growth of paper that they were published comparing 2010 and 2020. Among the different approaches, directed CH functionalization has emerged as a really powerful tool because due to the presence of a directing group in the starting material, it is possible to selectively functionalize a specific carbon on the starting material. These transformations are very atom efficient, and also thanks to all the knowledge that has been gathered over the past 2 decades on rhodium and palladium chemistry, right now it is possible to develop very sophisticated and elegant transformation. However, there is always room for improvement, and one of the main goals of the field is to move toward air-abundant ferrometal. And in our case, we have been focused on cobalt, not only in terms of sustainability, because it's earth-abundant and inexpensive compared to palladium and rhodium, because as other ferrometal, cobalt exhibit low electronegativity and can undergo multiple oxidation states through 1 and 2 electron processes. So just to give you an overview of the field, probably you know a little bit of this topic. The paper that changed directed CH functionalization was published by Murai in the early 90s with ruthenium chemistry in the functionalization of these ketone derivatives. However, this was not the first example on directed CH functionalization. The first one was published in the 50s by Murahashi using a cobalt precatalyst. However, these compounds were overlooked for almost 5 decades. In 2010, Jessica and co-workers started combining cobalt salts with Grignard reagents to develop what is called low-valent catalysis, to develop different different type of transformation, and just a few years later appeared what is now called high-valent cobalt catalysis, first by Kanai Matsunaga using CP cobalt complexes, and in 2014 the Gulis combined cobalt source and oxidant to access cobalt-3 that are the active species in the CH activation step. In our case, we have been working with this CP cobalt system that is surprising that they are known from, since the 70s because they were developed by Mechlis. They are completely analogous to the catalyst that, to the CP rhodium precatalyst that you can find in daily basis in the literature. And what is very interesting on this system is that they not only can emulate rhodium, they can also exhibit unique reactivities. And since the pioneering work by Kanai and Matsunaga in 2013, the field has flourished. And here I show you some of the main players, Lutz Ackermann, Subuk Chan, Jonathan Ehrman, Frank Loris, among others. The catalytic cycles proposed in the literature normally are cobalt-1, cobalt-3, or redox-neutral cobalt-3. And these systems are particularly good using electrophile coupled partners because after the CH activation, the carbon metal bond that is formed is pre-nucleophilic, so it's way more reactive than rhodiums in most cases. As the drawback is, as you can see here, there are really limited examples of nucleophilic complete partners, and I will come back to that at the end of my talk. So this is great from a synthetic point of view, but from a mechanistic perspective, when we started this project, it was really challenging to know something about the mechanism due to the reversibility of the CH activation step. So it was really difficult to understand the nature of the reactive species of the mechanism involved in this transformation, and when a reaction didn't work, it was not possible to know where the bottleneck was located. So I'm going to show you our first, the story that with the initial work that we have done with this cobalt system. So the first path, our first step was to set the basis. So we needed to get access to this catalytic cycle, and we wanted to synthesize and isolate the intermediate that are proposed in the catalytic cycle in this type of transformation. So since the CH activation didn't work at the time, we decided to explore one of the most important reactions in organometallic chemistry, oxidative addition. So just combining an oxidative addition followed by a higher extraction using a cobalt-1 precatalyst, we were able to isolate this cobalt cycle, this cationic cobalt cycle that is completely analogous to the widely used intermediate that are proposed after the CH activation. And indeed, we selected this 2-phenylpyridine derivative because if you check the scope in this type of transformation, the 2-phenylpyridine is the most widely substrate used to test their reactivity. And I would like to say that the acetonitrile is key to stabilize this intermediate because we try a bunch of different reaction conditions and ligands, and in this particular case, in the absence of acetonitrile, we were not able to isolate and characterize the compound. So we were really excited when we had access to this compound. So the next thing that we did is to test the catalytic performance of this compound versus the most widely CP cobalt-3 precatalyst used in the literature, because we thought, okay, maybe we have access and isolated this compound. Maybe that means that it's not as reactive as we would like to see. However, we were wrong. Our compound, our cationic cobalt cycle, is more reactive in this annulation reaction. That is by far the most widely reactivity performed with this type of precatalyst. We can reduce the catalyst loading to just 1 mol%, which is one of the lowest in the literature. And thanks to the presence of acetonitrile, we were able to observe a resting state under catalytic conditions that turned to be this 7-member ring cobalt cycle that is formed after the insertion of the alkyne into the carbon-cobalt bond. So that was the first example of an unreadably characterized transient species under catalytic conditions that it was reported in the literature. So we were really excited with this result. However, we came back to one of my obsessions in this project that you will see along my whole presentation, and it's the CH activation. Not only because from a synthetic perspective, that can facilitate a lot the access to more cobalt cycle, but also because if you think the CH activation is the only elementary step that is common to all the catalytic cycle, because the other steps depend on the coupling partners that you use. So basically, we thought a lot about this elementary step, and we thought if we can tackle the reversibility of the CH pentylation. And we came up now with a very simple and solution, but it took us a long time. So basically, the reversibility of the switch activation was telling us that it was equilibrium shifted toward the starting material. So basically, what we wanted to interrogate is we can shift the reaction forward, just putting all the knowledge that we acquired in our previous work and use it as acetonitrile as a stabilizing ligand. And we found the perfect candidate to test this hypothesis. This is other prevalent precatalysts using this cobalt catalyzed transformation that already contains the ligand that we were looking for. And long story short, when we combine our 2-phenylpyridine with this cobalt compound, we were able to synthesize the desired cobalt cycle. As you can see here, just at almost room temperature, we have full conversion in less than 1 hour and a half. Maybe now this seems very simple, but this took us a long time because we tried to mimic rhodium chemistry, and in our rhodium chemistry, this type of metallocycle are synthesized using carboxylate as base. However, in this cobalt system, when you use carboxylate, what you form are these dimeric species that are inactive under stoichiometric conditions. So this opened a new question: what happens if we want to use substrates that are less basic than 2-phenylpyridine? Because here we were using the substrate also as a surrogate base. And that is the case of this pyrimidine. When we use the same reaction conditions that work so nicely for 2-phenylpyridine, we discovered that it took more than 40 hours just to get 65% yield. Anyway, we were really excited because this was our second knowledge building block that we were able to synthesize and characterize. So after a lot of work, we discovered that when we add diterbutyl pyridine as base, we can speed up the reaction, so we get full conversion in 20 hours. But even better, when we combine this base and HFIP, this perfluorinated alcohol, we observe a very remarkable effect. So when we add one equivalent, the reaction is speed up 10 times, but when we added 50 equivalents, the reaction is done in less than 1 hour. Sorry, less than 5 minutes. So we wanted to know if this beneficial effect that we observe in the CH metallation could be translated to the whole catalytic cycle, and we selected, based on our experience with alkynes coupling partner, these two reactivities because they share the starting materials, but depending on the reaction conditions, you can have the annulated product of the hydrolylated one. Both share the CH activation and the migratory insertion step. We were able, again, to fully characterize the 7-member ring cobalt cycle that is formed after the migratory insertion. And after this, in the oxidative annulation, we selected, in both cases, a report that already were described in the literature. In this case, we pick the reaction conditions described by Liang co-workers in 2016, and using our cationic cobalt cycle as precatalyst and using a mixture of HFIP dichloroethane, we can reduce the temperature to 60 degrees, reduce the reaction time to 8 hours, and increase the yield from 64 to 91% yield. In this case, what is key, what makes so special the HFIP present is the polarity of the solvent, because it's key for solubilizing the copper and silver salt that, as I told you, they are not innocent, and they are not only key for the reoxidation of the cobalt-1 to cobalt-3 for the regeneration of the active species in the CH activation. What we discovered is that these salts are also key for promoting the reductive elimination step. And in the hydrolysation process, we also observed a very beneficial effect due to the presence of HFIP. In this case, we selected a paper by Sundararayu, and we can reduce the temperature again to room temperature, reduce the time, and here we observe a significantly increase in yield from 33 to almost quantitative yield, isolated yield. And in this case, the HFIP is acting as a proton source that makes this reaction so efficient. So we were really excited with this result, but so far, what I show you are a couple of examples using a starting material that contains strong directing groups. And we wanted to move what I call to real-world chemistry, and when I think about that, these are the type of molecules that come to my mind: drugs, agrochemicals that contain amide, ester, ketones, aldehydes. However, from an organometallic perspective, it's not trivial to synthesize metallocycle containing these functionalities as directing group, even when using novel methods. Indeed, in cobalt chemistry, there are, before we started our work, there were only a literature present, reported by Jonathan Enman in Nature Catalysis. The group described a beautiful tandem reaction, and they synthesized this cobalt compound in which it was using amide as a directing group, and the anion that they used, it was barf. So the yield are not great. The barf, we know that has very peculiar properties, but we were inspired by this work, and we thought if we can apply our knowledge to expand our library of reaction intermediate. We tried the CH activation, we failed. So far, we have not succeeded. However, when we apply our oxidative addition, we observe fantastic result just mixing the aryl halide with different directing group with this CP star cobalt compound in THF room temperature, just 5 minutes. That is basically the time that Sarah and Carlota just took the time to go to the NMR. We can see the formation of cobaltacycle containing aldehydes, ketone, amide, ester, 5-member ring, 6-member ring. All of these compounds are isolated, characterized. Most of them are stable, so we can work with some of them outside of the glove box. And also, we tested as precatalysts in already reported CH functionalization reaction, and I can say that are completely comparable to the widely used cobalt precatalysts used in those work. However, this project opened a new venue that we didn't expect at the time. So we were really focused at the time in the CH functionalization. However, so far I show you how powerful the oxidative addition it is for accessing our cobaltacycle. So we wonder if we can engineer or we can exploit this feasibility to undergo oxidative addition event to do catalysis, because cobalt chemistry in cross-coupling reaction has been used for a long time. Indeed, there are beautiful reviews by Gosmini and also by Catiet and others. However, CP-star cobalt precatalyst, cobalt-1 precatalyst remains unexplored. So, as a proof of concept in this project, we disclose this annulation reaction that seems very simple, and it is. However, it has a peculiarity. It enables the coupling with primary amides. In CH functionalization reaction using this type of cobalt system, it's not possible to use them. You need to protect the nitrogen, at least with one of the position, because otherwise you cannot do the reactivity. And I will come back to that at the end of my talk. So here we use cobalt-1 precatalyst, also one of our neutral cobaltacycle, and they work fairly for giving the desired transformation. So far, and at the beginning of my introduction, I told you that these systems are very powerful for coupling electrophiles, and that has a drawback. Just 1%, now less, of the papers reported in the literature involve nucleophiles. And when I say 1%, it's just 3 examples. One is a CH methylation reported by Lutz Ackermann in 2020 in Nature Chemistry in collaboration with AstraZeneca, that if you didn't know it, I recommend it because it's beautiful and the sachetoscope is just amazing. And the other 2 examples involve carbon-sulfur bond-forming reaction by Frank Glorious and Juan and co-workers in 2016 and 2017, respectively. So this caught our eye, and we wanted to know more, why are nucleophilic couplings so rare? And we selected the report by Juan as our benchmark system to investigate a little bit more this transformation, because, as I told you, I didn't have time to talk to you about our result on Konitz methyl, but we have some experience using silver nucleophiles as transmetallitic reagents. Also, and very important for us, the silver nucleophile that one use is commercially available, so we can, and also it's very easy to synthesize in the lab. So we have no doubt about the nature of the reactive coupling partner in the transformation, and also we love NMR to do our studies. So this SCF3 moiety has a distinctive chemical shift by fluorine NMR. So this was the catalytic cycle proposed by Juan and co-workers, and it's completely analogous to the one proposed by Glorious and also for Lutz Ackermann in the methylation process. And so what we did is, the first thing is to try to synthesize the neutral cobaltacycle that is formed after the transmethylation step, and we succeed. We have this compound, really high yields, and is stable at air and outside the glove box. the first surprise, or at least maybe now is not so surprising, is when we hit this compound under the reaction conditions that they were disclosed in the catalytic reaction, we didn't see any product formation. Indeed, the compound is very stable. So we came back to the paper, and what we realized is that the only big impact about the different components that are part of the catalytic cycle are the silver salt. So when we added 5 equivalents of the silver salt to this compound, and again we submitted to the same reaction conditions that are proposed in the catalytic paper, we observed in less than 1 hour quantitative formation of the desired carbon-sulfur bond-forming reaction. So far, or now I'm going to tell you a little bit more, our proposal is that what is having is that the silver is not only the nucleophilic coupling partner, it's also acting as an oxidant, promoting the access to cobalt-4 species that are the ones involved in the reductive elimination. And these results are in alignment with a related rhodium and iridium system published by Chan and co-workers and Blakely, that propose similar transformation for these novel metals. Indeed, we have confirmed the formation of these cobalt-4 species by electrochemical analysis, and also the oxidative-induced reductive elimination by DFT calculation, because when we compute in collaboration with one of my colleagues at ICIQ, Professor Felipe Maceras, the reductive elimination for from cobalt-3 is really high in energy. However, once that we have the cobalt-4, the energy is lower than 10 kilocalories per mole. Indeed, we have tested different oxidants, other silver salts that are not so great, copper acetate neither, but manganese 3 works very nicely in this system, and also when we perform bulk electrolysis, we observe quantitative conversion of the starting material to the product. So our result show for the first time the involvement of oxidative-induced reductive elimination in this type of CP star cobalt system, and the potential involvement of high-valent cobalt species in catalysis. And since then, we have been working a lot in this type of project, and we have explored another nucleophilic couplings, and spoiler alert, we are wrapping up a couple of papers. What we have found is that the systems are way more complex, and the mechanistic scenarios are more diverse than we could imagine at the beginning. So it has been a really fun process, but also tough to investigate experimentally. And I want to finish my presentation with some unpublished results. So as I show you, we have been trying to improve already known reactivity. So over the past couple of years, we have been trying to create new reactivity. We have tried to expand the synthetic toolbox of reaction mechanism and synthetic protocols, and also now we do metal-free transformation. And if you asked me a couple of years ago, I would not imagine, because we are in an organometallic audience, I'm not going to show you those results, but I'm going to focus on the ones that are related to the cobalt system. And as I told you along my whole talk, I'm very obsessed with the CH activation, because it was a big headache for a long time. But we tried to convert, to transform this mechanistic challenge in a synthetic opportunity and develop a deuteration protocol, because it's very surprising, but there are very few examples of directed hydrogen isotope exchange involving ferromethyl. Indeed, I think that there are 3, 2 involving manganese by Matthias Beller, and 1 by this CP star cobalt-free system reported by Thu in 2020, but the substrate scope is mainly done with rhodium, and they only use cobalt for maybe less than 10 substrate, and all of them are indole derivatives. So we wanted to expand the scope of this transformation, taking advantage of the reversibility nature of the CH activation. Very long story short, we have engineered different reaction conditions. For example, if we want to deuterate substrate containing strong directing groups, we just need to use deuterated water and 50 degrees. If we want to deuterate derivatives of aldehydes, we need to add catalytic amounts of amine to form a transient imine. And also, that was very surprising, under those conditions B, fall some substrates that we thought at the beginning that they were going to belong to condition A, but here it seems that we need a higher temperature. And under condition C, we are able to deuterate amide derivatives using deuterated methanol. This is cool, and we were very excited. However, the most exciting part of this work is that our result confirm a behavior that is widespread in the literature but is completely overlooked. That is that different starting materials requires different deuterating sources. And we were really intrigued by this behavior, because if you check the literature, the selection of the deuterated source is purely empirical. You are not going to find any directed hydrogen isotope exchange protocol, as far as I know, that rationalize why some deuterated source works and others no. So we have joint sources with a very close friend of mine, Professor Anat Miller at Ben-Gurion University of Negev in Israel, and Anat's group is an expert on developing statistical models that correlates function and extraction to identify the principles that govern reactivity and reaction outcomes. And what we have discovered is that it makes sense that we need different deuterium sources, because the mechanism that we have discovered is different depending on the substrate that you use. So this work is going to be, I hope, once that is already in Cambridge, if you want to take a look, it's already published, it's going to be the first time that try to rationalize why we need certain deuterium source under certain reaction conditions. And this is the last piece of information that I want to show to you today. In 2020, we showed that we can use this aryl halide as a very interesting substrate for CP* cobalt catalysis instead of using cobalt-3, using cobalt-1. And these results showcase something interesting, that maybe we can use this react transformation to functionalize substrates that are challenging through CH activation. So pretty much containing weakly directing groups that are not very successful for this type of reaction modes. We have developed peptide coupling as a proof of concept. For the alkene scope, we have selected ester derivative as the starting material, because if you check the literature, it's not so easy to functionalize ester, and indeed in situ activation with this cobalt system, there are only 2 examples, are kind of quite exotic. So we have been able to couple these esters with activated alkenes and activated ones, styrene, also with complex alkenes. This is, as far as I know, one of the broadest alkene scopes that you can find in this type of transformation, including situ activation. We can not only couple ester, we can also couple acetanilides, amide, carboxylic acid, ketones. We can also use bromides, and here we expand a little bit the scope of our directing groups, because they are more commercially available. And also we explore a little bit the functional compatibility, and as you can see here, it's particularly good for aryl halides containing donating groups. But the most interesting thing is, like, we can also couple chlorides. We are very, very excited, because this is not easy even with novel methods. So our methodology is orthogonal and complementary to CP* cobalt catalyzed functionalization reaction. We have a broad alkene scope. We have very promising results with aryl chlorides. I cannot show you the real deal, because the real deal is that we found a very unexpected mechanism. That is going to be a quite interesting paper, because it's going to be a mechanistic paper with a huge scope at the end. That at the beginning is not what we planned, but what we found in terms of the mechanism is way more interesting than the scope that I just showed you. And we have joined forces with a fantastic very talented young researcher, Ignacio Funes, that has helped us a lot with the DFT calculations. So this is the end of the talk. So I wanted to transmit my passion for mechanism, that we really think that they are really powerful tool for reaction design and discovery. They can drive catalysis, they can drive reactivity, and for sure they can drive new reaction pathways. And especially for this first row methyl, they can expand the mechanistic playground, because I really think that just we are seeing the tip of the iceberg, and this first row methyl, cobalt, already nickel is better established, but alone manganese, iron, I'm sure that they are going to be the key players of the 21st century, and I think that we are going to discover very interesting reaction modes, especially the ones that are unexpected. Of course, I would like to thank my group. I show you the faces of most of the students involved. I have a new generation. Half of the group, as I told you, they are not working with methyl, which is kind of weird. They are great, they are fantastic. We have very interesting things that we want to share very soon. I also would like to thank the collaboration. Some of them are with some of my colleagues in ICQ. They are fantastic. I always say that ICQ is like a Disneyland. So it's just you have to enjoy and use all the resources that we have around. I think that you are going to see along the week some of the results that I have been doing also with one of my colleagues, Arjan Clyde, in ICQ. I would like to thank, of course, the funding. And finally, we have an open position that is going to deadline is next Monday. So it's for a postdoctoral position. If you know someone, please, please, please tell that person if you're interested, submit the application. It's through the ICQ website. We are doing really interesting stuff, so we are really excited to enlarge the family and join new people. So, and if you want to know more, please shoot me an email and I will be happy to give you all the details. And again, thanks for the invitation. Thanks, Marta. Congratulations for putting together this and for keeping the nerves over the past 2 days. And all of you for your attention, and I will be happy to take any question.
Thank you very much, Monica, for all the passion for cobalt. Are there any questions?
Thank you so much, Monica, and you sold me the project. I would be your postdoc, but I'm too old, so I wouldn't be very useful. I have a question, because you explained very much about different things, but I had a question about the type of counter ions for your CP star cobalt-3, if you have explored differences. And then you were commenting on the additives. The role of silver was clear to me, the role of copper not so much. And if you thought as well about heterobimetallics, could that be in your design? Thank you.
Indeed, in that particular reactivity, that it's heterobimetallic, because my colleague Feliu Maceras was in parallel investigating the role of those methyl in reductive elimination with rhodium system, and he described heterobimetallic species as the ones that are triggered the reductive elimination. Yes, we have explored a lot the role of the additives, and I don't know if you mentioned something about the anions, and yes, the anions also play a role, a big role, because they pretty much determine the reactivity and the stability. So we can go to something that can be used outside the glove box to something that we cannot isolate. So yes, but we have way more things that are not published than published, because when you try to put together a story, sometimes it's not so easy. So I can tell you that we have almost 70 crystal structures, so we know a lot about these systems. But sometimes it's not so easy, again, to put together a paper. So it's more in-house work that now we are trying to disseminate in other projects that we have, and just show, also take into account this, because this is important. But yes, the Konitz method do a lot of things. So yes.
Thank you.
Yeah, thanks for the talk. I had a question about the role of the hexafluoroisopropyl alcohol in the catalysis. It seems like that has a really big effect on the kinetics of the reaction, and I guess from what I gathered from the previous work, it seems like you're in a regime where you're in some kind of thermodynamic equilibrium of deprotonating the CH bond. Does that somehow affect the Lewis acidity of the cobalt, or?
So we have a whole already paper, but it's not published, has been in my drawer for 3 years. That was done in collaboration with Stuart McGregor in Edinburgh. So pretty much what I show you, at least half of the work is done by my first PhD student, Jesus. Jesus went there to learn how to do DFT. And the problem is that we can only study that transformation if we use the cobalt compound that contains that acetonitrile. And what we discovered is that the rate determining step is not the CH metallation, it's the dissociation of the acetonitrile. And it seems that the HFIP facilitate that dissociation. So we weren't sure to put together a paper saying we want to study the CH activation, but see, we cannot, because it goes after the rate determining step. So that is still in my drawer.
Still
But
very
HFIP
relevant.
can do a lot of things.
Yeah, it's still a very relevant step. I mean, that would be interesting for the community to know about, I'm sure. But I didn't want to bring
Yeah.
up a sore spot.
It's like, it comes like cycles. So a new student comes and it's like, look, we need to finish this paper. And after a couple of things, we don't get any new information about the switch activation, so it's complicated. So, but maybe we give a new shot.
Well, to me, it still sounds very interesting. Thanks.
Thank you.
More questions to Monica?
Everything is super clear.
Then I go with a little one, even though this is not really the chair's people. But then I was wondering, in your catalytic cycles or in your mechanistic cycles, the silver always comes in very late when you have already done the oxidative addition. But often you start with cobalt diiodide or cobalt dichloride. Are you sure when the silver pops in, or could those ligand exchanges happen even before you have any?
Oh yeah, so
cobalt conformation?
So the thing is, in all our reported papers, I'm double checking, but yes, we don't use the traditional CP star cobalt diiodine carbonyl. So we don't extract any halide because we don't have it to start with. But of course, I'm sure that is important. And indeed, one thing that is my guess, supported by a little bit of, I guess, experimental results, people tend to ignore that extraction, everyone thinks that is easy, maybe it's not so easy. So maybe that can play in certain cases more important roles in the redetermined step that people think. So.
I saw the lights change to
Yes.
blue. Maybe there is a message behind the whole thing. So
We will stop here.
maybe we should close this session here. Thank the speakers. I think we had a wonderful start and a nice spark of as well women in science, and I'm sure we see much more of this during the course of this conference. So thank you, Monica. Thank you also, Paul. And our chair has some announcements.
Yes, just two very quick announcements. One is for the speakers that remember to hand in your talk, preferably in a PDF file. The speakers for tomorrow, if you can do it today or tomorrow at the earliest, please, to the technical secretariat. And also now there is the cocktail that is going to be outside in the court to the left. I'm not sure if it is going to be indoors or outdoors because I don't know if it has been raining recently, so we'll see exactly when we come out. And also remember that tomorrow the conference will take place in the campus. You need to get transportation, so we won't be here. Remember, it's going to be in the School of Engineering. And please check in the booklet all the instructions for where to get the bus, either the public transport or the bus shuttle that we have organized. Okay, thank you.